got some extra space in the, Or if you, if you want to follow me with like the stage cam too, that'd be fine, right? What's the structure on the front of your notebook?
Yes.
You don't know what it is? Or?
Doesn't have to do.
Oh, I gotta take notes. No, I just didn't know what I was on. But, all right, so here we are. We are making our way through the substitution and eliminations, and we're starting to kind of go through the process of distinguishing the different mechanisms that can occur. And the point is that pretty much all of the mechanisms can occur at all times, right? The conditions are not, at the end of the day, they're not that different for the four mechanisms. Because they all deal with, well, is there a nucleophile, is there a leaving group? Or is there a base, or is there a leaving group, right? But we know that bases can be nucleophiles, and so that's where the overlap starts to happen, right? And even weak nucleophiles can sometimes act as bases, and so we start to have this competition that's happening. And so the idea that we have to try and think about is not necessarily can we stop a mechanism, but can we slow it down to some extent that it won't happen, okay? And we can just kind of think of that as kind of stopping a mechanism, okay? But the point that we left at is we were dealing with one of these big ideas out of the SN2 mechanism, which is the idea of sterics, right? We said that as you add more junk around the carbon, right, as you add more junk around the carbon that the leaving group is attached to, it just starts to slow that reaction down more and more and more and more, okay? But it's also not just what's attached to the carbon that's bound to the leaving group, it's also what's next door to the carbon bound to the leaving group, right? And we said that as you, I believe it was up a little bit more, right? So as we start to add stuff next door, we'll slow down the SN2 reaction more. But not so much that it can't happen either, okay? But not so much that it can't happen either. But in the one on the right-hand side there, you know, we're asking a lot for that to do an SN2 reaction. But it could still happen under the right circumstances. Okay, so what does that mean for you guys? It means that what we're really trying to select is the idea of major versus minor products, right? Major mechanisms versus minor mechanisms, that kind of thing. Okay? Let me ask you guys a question then. Now, before I ask that question, I'll come back to it later. I'll save it for when you guys aren't paying attention. And then I get to trick you guys. And what does that mean? Well, you can't fail in class, if only. No. Right? But we'll come back and ask a question about this stuff. But keep this in mind. It's all about sterics and these things. Okay? Now I lost my train of thought. Shoot. What was it? Must not have been that important, huh? Okay. So let's move on to the next idea here. Oh, that's what it was. I got it now. Really shake things up. Okay? Why don't you guys come up with your major product, your minor product. You know, what are the mechanisms to get there, that kind of thing. Right? I'm sorry, Thomas. So what do we got?
E2 is a major product,
How'd you get that?
because, the lone pair bond with the next door neighboring hydrogen, and I figured there couldn't be a carbocation.
Well, that's the mechanism, right? So how did you get to that mechanism though?
There's a strong base present.
Okay, so there's a strong base. What else?
I figured it couldn't be, a carbocation couldn't form because it's, secondary flavor, and.
I would say it's less likely
Less
to
likely.
form, right? It could still form, right? But less likely to form,
So
okay?
that kind of eliminated SN1 and SN1 and E1.
Okay. It slowed them down for sure. Okay, what else?
Good leaving group.
Okay, got a good leaving group, it's secondary, strong base, right? All that kind of stuff is pointing towards a preference for E2, right? Cool. What would our minor products be then? What mechanisms? Could we form a carbocation? Yeah. So could we go through E1? Yeah. Could we go through this SN1, which we haven't really talked about, but you guys can already figure out how it's gonna work? Yeah, don't worry, we'll get to it, right? So all these mechanisms are in play, good. So let's take a look at the major product, okay? Let's take a look at the major product here. Okay, we look next door. Cool, all right. Got it. Fair enough. Now let's really change things up again. Okay. Let me rewrite this down here. I'm gonna need some space. So, this is the same thing. I just need space. For argument's sake, I'm gonna leave off the conjugate acid of our base there, but doesn't mean it's not there, it's just we're going to have to discuss some things. Okay, so I could ask you guys the same question here. Okay? And you guys would tell me that this is my major product. Okay? Cool. Fantastic. And now we use this guy here. Okay. So, what's the same and what's different?
Is the base sterically inhibited?
Yeah, what makes you say that?
Because there's more like ethyl groups coming off of the carbon that's
Mhm.
attached to it.
So the base is sterically hindered, extremely sterically hindered. Dragging a lot of emotional baggage along with it, right? A lot of methyl baggage. Do sterics affect how reactions work?
Yeah.
Sure, right? That's what we were talking about with SN2s, okay? Now remember, I tried to start to tie this together for you guys, right? SN2 and E2s, right, they have some similarities with them, right? In terms of sterics being one of the issues we need to pay attention to. That's what we're going to talk about here, okay? So we have a big bulky base. That's going to change things. So what is our product going to be for this reaction? Well, we do have a strong base, and we do have a good leaving group, and we do have hydrogens that are next door to that leaving group. So this is all setting up for an E2, right? There's nothing different about this. An E2 is going to happen, except our product is going to be this. I know. I can tell from your stunned silence that you guys don't believe it either. Some of you guys have masks on, so I can't see the look of horror behind it. But, thank you, Cole. Yeah, there it is. Right? What's different?
It's not tri-substituted.
terminal.
It's a terminal alkene. It's not the most substituted alkene. In fact, it's the less substituted alkene. Why? Why would something like this form? Well, got to deal with the emotional baggage, right? So if we draw the mechanism for this, yeah, we can do that. That should be all right. Let's do this, right? There's our hydrogens next door. Okay, our mechanism's still going to be E2, so we grab, pop that down, kick that off, right? Nothing different about that. But why does it want to go after those hydrogens?
They're the easiest ones to get to.
Yeah, that's really what it is, right? They are more sterically accessible, right? They are more sterically accessible. As opposed to these hydrogens here in green that have other carbons and methyl groups and all that kind of stuff around it. Does this make sense? So if we back up for just a second, okay? If we back up for just a second to this same idea here, right? Remember, we talked about here, if a nucleophile hits that carbon, it's got to move through all the trees to get to that carbon, right? The same, so this is just a visualization of how sterics work, right? So the same idea is dealing with that green carbon. That green carbon has all these methyl groups nearby and those other methyl groups on that other side. It's got a lot of forest around it. Now on paper it doesn't look that way, does it? So no, it looks pretty accessible to me, right? But remember, these things all have three-dimensional shape. Okay? These are all sp3 hybridized. There's lots of methyl groups around there. That's actually a fairly sterically hindered hydrogen. Okay? It's a pretty sterically hindered hydrogen. Can that base grab that green hydrogen? Yes, it can. There's nothing stopping it from doing it. But what do sterics do? They don't stop stuff, they slow it down, okay? In some cases, they might completely stop it, but you guys get the point here, right? It just slows down the reaction with that green hydrogen. So we would still have a minor product form, right? So our minor product would look like maybe what we would expect in green there, right? But we're going to have this as our major product, and that would be our minor. Sterics is going to slow that down. Make sense? So now let me tell you about my life. Because I've got a captive audience, and you guys have to listen to me yammer on about my life. Okay? All right, I'm joking. Let me tell you a little bit. Listen, so I'm going to give you guys a hint. Okay? Most of you guys have to go on to biochem, right? So when you guys get to biochem, if Dr. Barbosa is teaching it at that point, you guys, I'll give you the way to impress him. Maybe I should stop recording for a second. I don't want to give away my secrets. When in the world of chemistry, there's always two smart answers to begin with, okay? For really anything that I ask you guys. The two smart answers are sterics or electronics, okay? Sterics or electronics. And what I mean by that is the phenomena that we observe, the mechanisms that we go through, the reactions that we see, okay? All these kind of things are really governed by sterics or electronics. And so if you're ever stuck on a question and you're in biochem and he's talking, I don't know, what do they talk about in there? Proteins, okay, right? Right? And they're saying, why does this protein behave in the way they do? Right? The good place to start would be sterics or electronics. And you'll be right, I would say 80+% of the time. Okay? Not too bad. Now, as I have maybe admitted, so you guys are maybe not on camera, I'm a dum-dum, but I can remember two things. I can remember sterics and electronics. Now, of course, as soon as you guys answer that on the exam, what am I going to ask you next? Why, right? And that's where it gets complicated. All right, he actually expects me to know something, right? Okay, right? But that's it, right? If you are stuck on something, right, and you go, I don't know, I can't remember this. Start to work your way through this. Sterics has to deal with things bumping into each other, things that are crowded. It slows certain things down, prevents things from getting close to each other. Okay, that's what sterics deals with. Sterics is why Cole sat on that side of the room and you guys all sat over here. Okay. I mean, that's not a good example. I don't know why, but you guys get what I'm saying, right? Sterics is socially distancing for atoms. There we go, right? They want to stay away from each other, okay? That might be the other way of saying it. Electronics deals with where the electrons are. Have we been talking about where electrons are in this class? Yeah, in fact, it's pretty darn important. What have we been asking? Is this a strong base or is this a strong nucleophile? And one of the ways that we deal with that is by looking at whether it's a disperse negative charge, right? What are we dispersing? Electrons, right? Do you guys get what I'm saying here? Do dispersed electrons behave differently than localized electrons? Yeah, right? That's what we're talking about with electronic effects, okay? It really narrows itself down to two of those. Then if you want to get super fancy, you say relativistic effects. Okay, wow, but that one's pretty rare. Okay, but if you strike out on the first two, go for that one, right? Okay, but anyway, so really that's where all of your guys' arguments should start. As much as I'm joking with you guys, I'm really not joking all that much. I promise you, a lot of the chemistry that we deal with comes down to those two arguments. It's a steric or an electronic effect. Now we should be able to wander through the woods to figure out what each of those things implies or what it does or how it affects it, okay? But those are always good places to start, okay? So, in this case, sterics is what's taking over and the fact that it's a strong base. So we have a mix of the sterics and the electronics here. But sterics is the one that's dominating the distribution of products that we see in this case, where the red product there with the red double bond is going to be the major organic product. Okay? Now this is useful for us, extremely useful. Why? Why is it extremely useful to be able to use this base? What's the benefit of this? Every other elimination we've done, we always do what? Our product is always the most substituted double bond, right? Have we figured out any other way to do it? No. How many reactions do we know now that makes our less substituted double bond? Just one, and it's what? This one. You guys with me? Do you think that's pretty darn important? Do you think there's a lot of important reactions that happen that we need to put a double bond on the less substituted side? You bet. Okay? You bet. Yep.
If you were to draw the enantiomer of this molecule, would it attack the hydrogens that are on?
Enantiomer?
Well, I guess if you were to draw like the mirror image of it, and
it's not a chiral center.
Oh, okay, well that's true. But
Yeah.
is there? I guess what I'm saying is there equal chance that it'll attack the hydrogens on?
Why to pick the ones on top versus the ones on bottom? Is that what you're asking? Why to pick those instead of the ones here?
Yes.
What difference would it make? That's my question back to you, right? What would the product look like? It's a good question. What would the product look like if I attack those ones on the bottom?
Well, the double bond would go on the left side.
Okay.
Across from the.
So, right, you're saying this, right? Right. Okay.
So I guess.
What do we know? What do we know about every single bond? It can what? Free rotation, right? So if I just rotate around this here, right? So if I just rotate that, What does that look like? This is that, right? So they're the same. Those are equivalent methyl groups. So if you think about what we talked about with our NMR discussion, where we have like symmetry within molecules where hydrogen domains or hydrogen environments are the same, that's what we're talking about here. Those, the hydrogens here versus the hydrogens there, those are equivalent. We wouldn't see any difference with those because it's not a chiral center, right? So they're equivalent positions you might want to think about like that. Okay? But it's always a good idea, right? Draw those both out and then go, right? What's another way of figuring out that those are the exact same molecule?
You can do a mirror image and if it overlaps or if it's like.
Yeah, you could do that, right? But that's still a visual way of doing it, right? That would work. What's another way of doing this, though?
Or RNS.
Hmm?
Like if it's a chiral center, you do RNS.
You could, but these are, no alkenes can be chiral in the sense, or excuse me, they can't do RNS, right? How many Patrick Christopher Hillesheims are there on this planet? Just one, right? How do I know that there's just one? Well, I identified it by my name. What's the name of the red and the pink versions up there? Well, we'd have what? 2-methyl-1-butene, right? Would the name be the same for both of those products? Yes. If they have the same name, then guess what they are? The same compound. You guys with me on this one? Right? So if there's ever a doubt, just try to name it. If you come up with the same name, then there you go. Okay? Now, what does that rely upon? You guys knowing how to name it, right? But that's the idea, right? If the name comes out the same, then we know it has to be the same product there. Okay? Cool. All right. So let's think. So, Kate, what do we got?
I did an E2.
Huh?
I did an E2.
Okay, so give me your evidence for the crime.
We have a pretty good, it's a pretty weak base. Is that?
A pretty weak base?
A very weak base.
A very weak base. What makes a weak base?
The localized negative.
A what?
Localized negative.
Other way around. A weak base is a delocalized negative. So we don't have a weak base, we have a strong base, extremely strong base. Right? That's one of these key things to look for if you're going to do an E2. You catch that?
Yeah.
Okay. If you do an E2, you need a strong base.
Yes.
What else?
A good leaving group.
Okay, do we have a good leaving group?
Yes.
Okay, what flavor of leaving group is it?
Primary.
Ah, interesting. Right? Could an E2 happen? Do we have all the ingredients to make our E2 cake? Do we have our strong base? Do we have a good leaving group? Do we have hydrogens next door? Right? Do we have all those conditions? Yes. What else do we have conditions for though? SN2. What are the conditions for an SN2? Good nuclear. Do we have a good nucleophile? Yeah. Do we have a good leaving group?
Yeah.
Yeah. What's the important condition for an SN2?
Very fast when it's primary.
It's fastest when there's the least steric hindrance around, right? Can we get less sterically hindered than a primary? You could, right? But there's only one example of it, right? So in general, can we get less sterically hindered than a primary? In fact, we have a primary with nothing really next door, right? So could we do an SN2 here? Yes. Which one's going to happen? Both, right? So the question comes down to which one's going to happen more frequently. Okay? Now this one's tough. Well, it's not tough, but I'll ask you guys a difficult question in just a second. SN2 is going to be preferred here. Okay? Why? Why might that be? Yep.
Well, if you do an E2 here, the double bond will form with only, it'll be like, I guess mono substituted,
Okay.
or is that right?
Was that? I was just seeing if you were done or not. That's
No,
all.
I think that's all I got.
Okay. No, that's good, right? So my product here, right? For my SN2, just to draw it out. Whee, right? I like to imagine that the atoms go wee. I want them to have fun. On the top there we got SN2. Always be careful. Don't go on your carbon diet. Right? Don't lose carbons. Why would an SN2 be preferred? Sterics isn't an issue. Right? Are sterics an issue? No, we don't have a bulky base, right? We don't have a bulky leaving group. So if sterics isn't an argument, then it must come to electronics, right? Jeez, you guys forgot what I just rambled on about for like 10 minutes there? Electronics, sterics, right? Okay? If sterics isn't the argument, then it's got to be electronics. So it's got to be something with my products, right? What am I doing in a substitution? What kind of bonds am I making? Sigma bonds. What are the strongest kinds of bonds that exist in general? Sigma, right? What am I making in my E2? Pi bonds. What's stronger, sigma or pi? What releases more energy? Sigma. You guys with me on this? So the electronic argument is you're creating sigma bonds in my SN2 reaction. But in your E2, you're kind of breaking sigma bonds, right? You have to remove a carbon hydrogen to make a carbon-carbon double bond. Okay? And you have to break the carbon-bromine bond. But you do that in kind of both cases. So the argument for an SN2 is electronic. You're making stronger bonds. You're making more sigma bonds. Okay? Both of these reactions take about the same amount of time in terms of kinetics. What's the slow step in both of these? What's the rate determining step?
They both have,
Hmm?
they both have the same. They're both considered.
They're both conserved, so how many steps are in this mechanism?
One.
Just one, so which one's the rate determining?
Yeah, it's-
That one, right? There's only one step, so it's gotta be that one. You guys get what I'm saying with this? So we can't say anything kinetically, but there could be an argument made about entropics, right? You did say that at higher temperature, eliminations would be preferred. But I didn't specify temperature for you guys, did I? No. So can't really make that argument. So we would make our argument based off of energetics, aka electronics. We say we make more sigma bonds, therefore that would be preferred. Okay? Therefore SN2 would happen. Fair enough? Okay? Would we still get some eliminations? Yeah, right? Yes, we would, right? SN2, I should be careful of colors. SN2 for this and E2 mechanism for that one, right? What mechanisms won't happen?
E1 and SN1.
Why?
Because the carbocation will never form on a primary.
Modify your statement a little bit.
It's very rare.
It's very, very what?
Rare for a carbocation.
It's very, very slow to form, right? Very, very, very slow form. Energetically, right? Electronically, forming a primary carbocation sucks. Okay? Sucks. It's going to be very slow. It's going to take multiple steps. How many steps are there in E2 and SN2? Just one, right? Forming a carbocation is always going to be a slow step. And it's made even slower, right, if we have to form a primary one. Good? So practically speaking, we won't see any SN1 or E1 form here at all. Okay. Boy, it only took 20 minutes to explain one problem. The next exam is going to be fun. Yeah, I want to grade it. Just F's for everything, right? It is, I'm sorry, I tried my best. Like, wait. Jeez, I had a crowd in here. You know what James 3:1 says? It's one of these very important statements that I always keep in mind. It says, beware, not many of you should become teachers, for you'll be judged more harshly than others. Right? Same. It's very true. So, Abby, what do we got? Hmm. Okay, give me your evidence for an SN2.
I was worried about because I was kind of worried about the stairs of it.
That's a pretty important part of SN2s, right? In fact, what does increased sterics do to the rate of an SN2? It what? I just can't hear you is what it is. I'm not trying to...
That's it? No, you're good.
It decreases it, right? It slows it down, right? So we've got a question between SN2, and usually it's twin brother of E2 then, right? Do sterics affect both of those? They could, right? Could. Let me ask you a question. So what's the mechanism for the SN2 here? We take one of these lone pairs and we hit what? That carbon, and we would pop that off, right? Good? Let me ask you a question. Oops. Oh well, I wrecked it. Darn it. I was gonna make my point, but I ruined it. But I think you guys get the point. Which one of those is easier? AKA, which one of those are gonna have less sterics involved with it? Hmm?
I think the red one.
The red one, huh? What's the red one hitting? What atom is involved with it? What atom is getting hit by the lone pair?
Carbon.
Carbon. What does it have to move through to get to that carbon?
I don't know.
A lot more stuff, right? What's getting hit in the green? Hydrogen. Where are hydrogens? They're always on the outside of things, right? In fact, to get to the carbon, what does it have to do? It has to go through those hydrogens to get there, right? It's got to push the hydrogens out of the way. But what if it just goes after the hydrogen itself? Are sterics really involved with that? Somewhat, right? Somewhat. But to a much lesser extent than if we have to go after that carbon. You guys get what I'm saying with this? So what's going to be preferred in this case?
The E2.
E2, right? In fact, it's a pretty drastic change. E2 is pretty heavily favored in this case. E2 is pretty heavily favored. That T-butyl group, that T-butoxide, the O with the minus charge with the chicken foot, right? T-butoxide. That is a very bulky base. It really slows down SN2 reactions. Really slows down SN2 reactions.
I have a question.
Yeah.
Why wouldn't the E2 go for the hydrogens on the one that the SN2 is?
Yeah,
Hydrogens attached to the.
good question, right? So why wouldn't it do that?
Well, I guess, my thing is because it's not, di-substituted.
What gets left behind if I take those hydrogens off? I'm saying, what if I make it act like an acid, right? That's what you're asking me. So if I take one of those hydrogens off, what gets left? Oops, I should red in color, I guess. What gets left behind? Right? Carbon with a lone pair and a negative charge. What's the pKa of an alkyl hydrogen?
Isn't it like 14 to 16?
It's about 50. The answer is it's really darn high, right? So that is an extremely weak base, which makes an extremely powerful, that's an extremely weak acid, which makes an extremely powerful base. So if that would happen, it would instantly grab that hydrogen back from the oxygen, right? It wouldn't even, it would just instantly grab it back. Right? The equilibrium favors heavily towards the O with the minus charge, okay? Because that's it, there's nothing else we can do with that, right? We couldn't eliminate or kick anything off or do any other stuff. That minus charge is stuck on that hydrogen. I mean, excuse me, on that carbon. Okay? Now, variety is the spice of life. Okay? And if we just went around using T-butoxide all the time, then life is boring. And then I couldn't make you guys miss as many problems as I want to on the exams. Okay? So I have to make it extremely complex. So LDA is another base that we need to pay attention to, okay? We'll see it crop up from time to time, a little bit more in the second semester than in the first semester. But that doesn't mean it doesn't have its purposes here. So LDA stands for lithium diisopropyl amide. Lithium diisopropyl amide. LDA. That's what it looks like. Okay. So tell me what you notice.
Looks non-polar.
Hmm?
Looks non-polar.
It's got a minus charge. It's kind of harder to get polar than that. Right? But what you're saying is it's got a lot of alkyl groups on there. Right? And that's an interesting, so hang on to that thought for just a second. Right? What do we notice about it?
It's like ionic almost, but like there's two different compounds with charges on it.
Well, our other stuff had charges on it too, right?
Is it
In fact,
separated?
all bases have to have charges on it. All good bases, right?
But it's like separated from the lithium.
Well, I just drew it there, right? They're in reality, they're probably a little bit closer together, right? Don't let that trip you up. So, I have stumped you guys with science questions. We're lost in the quicksand of organic chemistry. And we're desperately seek for two, perhaps, good answers to begin arguments from.
Sterically hindered.
Ah, okay. It's sterically hindered. What do you mean?
It's got, like, a lot of methyl groups on them.
Yeah, it's got 4 methyl groups around, right? That's central nitrogen. That's pretty darn bulky. Really darn bulky, in fact. Okay, what else do you guys notice?
It's got 2 lone pairs.
Well, oxygen has 3, right? Chapter 4. What did we talk about? What's chapter 4 all about? Acids and bases, right? Is this a strong base? Well, not everyone at once. Is this a strong base?
Yes.
Yes.
Yes. Is it stronger than an oxygen with a minus charge? Ooh.
No,
Hmm?
no,
Why?
because oxygen can better handle the negative charge than the nitrogen.
Okay. Okay, so oxygen can handle a negative charge better, so it can disperse the charge better, which would make oxygen a weaker base. Oof. Oh no. Let me ask you guys a question. When an oxygen with a minus charge acts as a base, what functional group does it turn into? O with a minus grabs a hydrogen, turns into
Alcohol.
an alcohol. Okay? N with a minus charge grabs a hydrogen, turns into an amine. Strong bases come from weak acids. Okay? What's a weaker acid, an amine or an alcohol? What's the pKa of an alcohol?
16,
About 16-ish. What's the pKa of an amine?
12.
Go ahead, somebody look it up real quick. pKa of amine. Who's got their computer up? I'm gonna go with, huh? 10? No. No, it's somewhere in the 30s. Let's see here.
Yeah, PK.
Of the conjugate acid. Yeah, the conjugate acid.
38.
38. 38? Holy crap. Are amines good acids? No, they suck. But if I do deprotonate them, what do they make? Powerful bases. Extremely powerful bases. Okay? Much stronger base than oxygen at the minus charge, in fact. Okay? So we've got a really powerful base. Okay? That's extremely bulky. More bulky than the T-butoxide. Okay? So what does that tell you about LDA here? It's really going to favor what type of reactions? E2s. Okay? Pretty much never going to see any substitutions with LDA. Okay? In fact, that's one of its purposes in life, is to completely shut down SN2s and help us only do elimination reactions. It's a powerful base, so it's really on the hunt for acidic hydrogens. In fact, later on, we're going to use this to deprotonate alkyl hydrogens, but only special ones, only in certain positions. So we'll see LDA come up quite a bit in the second semester. Okay? But this is an extremely powerful base, and I put it in the presence of a primary leaving group, right? A bromine on the primary. So what's our product going to be for the reaction there? What do we got? Primary leaving group, extremely bulky base. What are we all pushing towards? E2, right? How's the mechanism look? The same, right? There it is. Mechanism doesn't change, right? That's the whole point of a mechanism. Mechanisms are kind of our constants, right? They're always going to behave in the same way. The bases might change, the leaving groups might change, the substrates might change, but the mechanisms don't, right? Good? All right. Now that we've beaten all that to death, let's talk about our last mechanism, for this at least. Talk about our SN1s. All right. So, SN1s, again, we're going to be dealing with substitutions. It's going to involve nucleophiles, right? SN, right? And the 1 means that it is unimolecular in the rate determining step. Now, E1 is also unimolecular in the rate determining step. And what's the rate determining step of an E1? Formation of the carbocation. So what's it going to be here? The exact same thing. Got it? So, what are the conditions for an E1?
It needs to be like a tertiary, or it said favors more substituted carbon. Just
It happens more frequently on more substituted, right, carbons. Why?
Because you can generate stuff.
oh, so the carbocation isn't.
Mhm. So any carbon that can help stabilize a carbocation, right, will speed up an SN1 or an E1 reaction. Right? What else do we need to do in E2? Excuse me, in E1. You need a good leaving group. Not going to be any different for SN1, right? Good. What else do we need for an E1? If E2 requires strong base, E1 is
Like a weaker base.
not a weaker or a very weak base, right? A significantly weaker base. We see crappy bases. And then we say maybe an E1 happens. Remember, all your eliminations are acid-base chemistry, right? Strong base for E2, garbage base for E1, okay? So now we take this idea over to SN1. SN2s, we have a strong nucleophile. SN1, we need a weak nucleophile. What makes a nucleophile weak or strong?
I guess, like fewer lone pairs or like a lower dipole moment or something.
Okay, what's that all based off of?
Whether or not it's a localized charge.
Hmm?
Whether or not it's a localized charge.
That's part of it, right? What kind of charge though?
Negative.
Negative, right? If we've got a delocalized negative charge, we usually tend to make good nucleophiles, right? Soft negatives is what we're looking for. Big squishy negatives. But anything with a negative charge can be a nucleophile, right? Because what do we know about strong bases? They're also good nucleophiles, right? But they prefer to do acid-base chemistry just because those tend to be quicker and energetically favored, right? Cool. All right, so we need weak nucleophile for SN1, weak nucleophile, good leaving group, tertiary positions, all this kind of stuff, okay? And then we do an SN1. So, quintessential example. See what you guys come up with as your product. Knowing what you know about E1s. exceed the 5 carbons. So that would be an E1 or an E2. Pretty sure. Cool, there it is. Okay. What did you forget here though? Something important. Mm-hmm. Yeah, so is it gonna stop there? Is it ever gonna stop with an option or a positive charge? So keep going, see if it's okay. Cool. Where'd you get that from? Where did OH come from? Or did you just forget to write another heading? Oh, that's a pretty good way to put it. See, we got operas. The nucleophile attacks the cortical. Oh, it's another tragic opera, yes. I hope that's the professor. Yeah. The leaving group breaks its bond. Ta-da! Don't worry, I'm used to making a fool of myself. And that's what happens when you're a professor, right? All right. So, right, first things first, leaving group leaves. Anyway, leaving group leaves, we generate a carbocation. What do we always have to do whenever we generate a carbocation? You have to go, right? What do we think about while we're hmming it up? Any shifts, any rearrangements, any of that kind of stuff, right? If you don't stop and go, what happens? No, med school. You miss stuff on exams, right? Don't do that. Stop. Just get in the habit of stopping, looking next door, right? As you guys go through practice problems, I know we kind of get into habits and just, oh yeah, zip through and do this, right? Just get in the habit of stopping and taking a look, right? We're at a tertiary carbocation. Everything next door is primary. There's not going to be any shifts or rearrangements. Got it? Good? So now that we have the most stable carbocation, what happens next? We have a positive, so something negative has to come in, right? Well, we don't have something that's fully negative. We've got a crappy nucleophile. We've got water. Is water a good nucleophile? Nah, it kind of sucks. Can it be a nucleophile, though? It doesn't have a full negative charge, but it does have what? Partial negative, right? So let's bring in some water. Cool. All right, then we're done. Everyone knows that oxygen loves to have positive charges. That seems stable, right? So we'll just leave it like that, right? Mission accomplished. All right. No, right? Are we ever going to see an oxygen with a positive charge at the end of this? Not like that, right? Certainly not like that. So what happens next?
Another water molecule.
Yeah. All right, and what we end up with is an alcohol, right? Cool. Good. There's our SN1. how would the conditions be different if we wanted to do an E1 instead? Would the first step of this mechanism change?
No.
No. What's the rate determining step? Formation of the cation. So when the question comes down to SN1 versus E1, if one of them happens, the other one's going to happen, almost to an exact same amount. Got it? Why? What's the rate determining step? Formation of the carbocation. You guys get what I'm saying with this? If that's the thing that determines the rate, and that step is the same for both mechanisms, then after that it's just kind of a rush to the end, right? Because the slow step is the rate determining step. So typically it's really, really difficult to stop an E1 from happening if you're trying to do an SN1 reaction. Now we can favor these in some ways, and we'll talk about that. We'll talk about that in just a little bit, right? But I think that's a good stopping point for now, right? We can go appreciate opera. Sounds like Bocelli, right? Impressive. So anyway,